Hi, good evening, everyone. Uh, Welcome to the problem solving session number 4 of linear algebra through geometry. Okay, and this is the week 4 problem solving session. Okay, and yeah, I forgot to tell. Okay, so mine. Okay, my name is Bhavya. I'm a PMRF scholar from IIT Madras. Okay, and these sessions are held every week on Tuesdays from 6 p.m. to 8 p.m. Okay. Okay, good. So I'll begin the session directly. So yeah, I again looked at the assignments, and assignment 4 is not due yet. I looked at assignment contents of 2 and 3, and I do not personally, I do not think that there should be a problem. Okay, so even 3, I was considering actually discussing, say, assignment 3, but I still thought it is somewhat doable and also a repetition of the things we had done already in the problem solving sessions. But if you have particular questions about previous assignments, then just let me know. Okay, otherwise we'll just move on discussing about this week's content. Great. So what is this week's content? Okay. Week 4 content. Okay, so what is week 4 content? Well, this is the first time that we are looking into 3D. Okay. And now what in 3D? Well, 3D vectors and 3D planes and orthogonal, more on orthogonal projections. We did a bit last time, but this is just a generalization of last time's content from 2D to 3D in 3D. Okay, and there is another interesting thing now, that is the cross product and properties and its properties. Okay, so these are the things that are relevant right now. There was also a final section a bit on lines in 3D, but it was just a bit, and it is not the main focus of this week's content, so I won't be discussing it right now. Maybe next week we'll do it in detail. Okay, now we already saw vectors in 2D, right? So 2D vectors, okay, they are of the form, A, B, and yeah, I guess you can already tell that there is just two dimensions, say x, y, sometimes represented by e1, e2, e3, and so on when we run out of letters. But so we have x, a, b, meaning y-axis, x-axis, a, b, meaning that its projection on the x-axis is a and its projection on the y-axis is b. Okay, now we are looking at 3D vectors. So now what we have is an extra degree of freedom, meaning that now there are three axes, okay, and which corresponds to the world we live in, which is x, y, and z. So there is this. It used to be the let me call this x and y. This is x, this is y, and now I have this additional dimension z, and this z represents the depth in our dimension. Okay, so not only can points exist in this plane, but now imagine that there are infinite planes here. Okay, and each of those planes are indexed by a different value of z. So this plane belongs to z equals 10, and this plane belongs to z equals 8, and so on. and the origin, the one corresponding to the origin, that plane belongs to that equals 0. Okay, and so on, and therefore you have vectors that can actually exist in some other dimension, in the third dimension, and the projection of this vector in the third dimension, okay, which will look like it's okay. This vector will be harder to show because I need to show what the depth means. So if the vector looks something like this, then now I have this additional projection onto the z-axis also, okay, which was not the case before. Before there was only a projection towards the y-axis, and there was only a projection to the x-axis, okay, which will be sort of like, or rather the xy plane. That is enough, because this is too much skewed to the other side. So the xz plane, whatever. Okay, just wanted to do a quick recap. Okay, now let's look at the questions. Okay, we'll directly go and look at the questions. So now it's about linear independence. Okay. Okay, here's a simple question. So check if the columns are linear independent or not in these following matrices. Okay. So it's a rather simple question, especially the first one. So yeah, go ahead.
Okay, so I'm in 2, 3 and 3, 2. So I cannot represent one column as
Yeah.
some combination of the second column. So I mean both are linearly independent.
Both are linearly independent. Okay. Okay. Any other uh, answers from anyone else?
So basically, as we are speaking about now on the 3D, right? So if we can't
no,
express,
first only this. This is 2-dimensional.
okay.
Okay.
So if we the multiples of one vector can be expressed in the other vector, then we call it as a dependent one.
Exactly.
It's not.
Exactly.
This is in 2D.
So is it in 2D? Yeah, this is in 2D. So that's right. So you consider this to be a collection of two vectors. So this is v1, this is v2. Okay. And if it so happens that v1 can be written as a multiple of v2, okay, then linearly dependent, otherwise independent. So now the question is, can you write 2, 3 as some k times 3, 2? So that is the question, right? So let's see if that is possible. So so this would imply that 2 equals 3k and 3 equals 2k. Okay. Now if I solve this, okay, if I solve this, then what will I get? K equals 3 by 2. And if I solve this, I get k equals 3 by 2.
So in the first case, that would be 2 by 3.
2 by 3, yeah. Where is it? 2 by 3? 3k, 3k.
First one.
Okay, yeah. 2 by 3. Thanks. 2 by 3. And here k is equal to 3 by 2. Right? So they don't match, but we want just a single point of intersection, right? And this is one way to interpret it. I mean, the other way to interpret it would be, I mean, drawing lines and then finding if they have a point of, if they are parallel or not. Okay, if they are parallel or not. And is there any other creative ways to do this? Are there any other creative ways to do it?
So the first vector is two steps towards the x-axis side and 3 axis towards the y-axis side.
Okay.
Uh,
Okay, let's see. So,
and the second one would be 3 steps towards the right side and 2 steps upside.
okay. So the other way to do it would be like Goel says, 2 steps to the right side, and let's say this is 3 steps to the top, and the second vector, which is 3 2, would be 3 steps to the right and 2 steps here. This is what you mean, no?
Yes.
Yes.
And
You
now whichever scalar I use, I would be moving in the different directions, and these directions will never meet.
right. Good. So if you multiply this by k, okay, this vector, this will either be extended to a longer vector in the same direction, or it will be shortened in the same direction. Similarly, if you multiply this by k in one direction, either it will go like this, or if you multiply by a smaller k, it will go here. It can never happen, okay, that the two will coincide. And that is what you mean by linearly dependent in a 2D scenario, right? Because what you are saying is that an extension of, when extending V2 by k factor, you get V1. But that is not the case. So this is a very intuitive and graphical way to do it. Any other way to do it? There is another way to do it, which is yeah, good.
So we take we equate everything equals to 0, and then we can show that the sum would be equals to 0 only if the k is equal to 0, and there is no other way to make the entire thing is equal to 0. So v1 plus kv2 is equal to 0, and this can happen if and only if k is equal to 0.
Say it
and
again.
there is
Say
no-
it again. Say it again.
So we can write say v1 plus kv2 is equal to 0. Let us assume.
V1 plus kv2
yeah.
like this.
Yeah. V for vector and
Oh,
yeah.
okay.
Yeah.
Okay.
V1
Plus
yeah,
kv2.
V1 plus kv2 is equal to 0,
Hmm.
and if we can show that this would be equals to 0 if and only if this would be equals to 0 if and only if k I need to show that similar to the linear independence thing, that the entire thing is equal to 0. This can happen if and only if both the so you write say k1 v1 plus k2 v2 is equal to 0,
Okay.
and this entire thing would be equals to 0 if and only if both k1 and k2 are equals to 0, and there is no other way.
You mean
You multiply
k1
v1.
v21 k2
No,
v.
no, not in this way, but in the first equation itself, you write say k1 v1 plus k2 v2.
Oh,
The
okay.
coefficients of the vector
K1
v1.
v1 plus k2 v2 like this.
Yes.
Okay.
And this entire thing would be equals to 0 if and only if both k1 and k2 are 0, and there is no other way. No k1 and k2 exist, and which will make this expression is equal to 0.
But what are k1 and k2 here?
So k1 is a scalar multiple of say v1, and k2 would be the scalar multiple of v2, and
Oh,
this
okay.
entire thing would be equal to 0 if and only if both k1 and k2 are 0.
Oh, okay. But what if say either v1 or v2 is 0 vector?
So both should be equals to 0, or both will not be equals to 0.
Okay.
What if v2 is equal to 0? Then it will. It's satisfied that k1 should be equal.
That's right. Okay. Yeah. Okay. Interesting. Yeah. Nice. Okay. This is definitely one way. You can come up with several various ways to do it. Another way I would tell you is, it will be a more complicated way, but if you have two vectors, then they'll have an angle theta between them, and you know that theta will be equal to cos inverse length of what I've written, v1 v2, length of v1, right, times length of v2 divided by dot product of v1. So if you find theta and theta is not equal to 0, then you know that if theta is 0, only then will they be in the same line, and then therefore they'll be linearly dependent. Okay, is that all? Oh, okay. There is one final way to do it. I mean, that at least that comes to my mind, and that is 3, 3, 2. No. That is find the rank. How do you find the rank? Well, you'll use Gaussian elimination, no? Or you'll use what was that called, Gauss-Jordan, and get it to reduced row echelon form, and then see the rank, and the rank will tell you what is, whether, since the number of rows and columns are the same, it will tell you what is the number of linearly independent columns or equivalently rows in this case, right? So that is another way to do it. So I'm just saying that the same problem, there are several various ways to look at it, and solve, you'll get the same answer. Okay. Now this question: check if the columns are linearly independent or not.
So the idea of rank has not been discussed yet. So I hope that you would be explaining this rank as well, because rank has not been covered. You stated rank once while discussing the Gaussian elimination. I vaguely remember, but yeah, formally the rank has not been defined.
Oh no, we defined it. No, remember we said the number of pivots. Number of pivots in the reduced row echelon form or the row echelon form.
Oh, so probably I forwarded. Yes. I hope if you can quickly explain that stuff through some example or somewhere in like that.
Okay, yeah, sure. I mean, like, if you have a matrix, you remember Gaussian elimination, right? So if you if you have, let's take this matrix only: 1, 4, 3, 2, 5, 3, 6, 3, 6, 3. Okay, 1, 4, 3, 2, 5, 3, 3, 6, 3, 3, 3. Yeah, 3, 3, 3. Okay. Now it is difficult to tell whether there is a linear combination or not. Right?
Yes.
It's difficult. It's quite difficult. Maybe if you look hard enough, it will be clear. Yeah. Okay. There is a way to do that. Okay, but let's not directly jump to that. Okay. Oh, okay. So then it must be. Wait, just a moment. Sorry, one moment. 4. Okay, this is not 3. Okay, this should be 2. Yeah. Okay, that makes. Okay, so this is 2. Okay. Now, how did we do it? Well, we did. We subtracted, right? Let's remove the bottom row. Okay. So, or should we remove? Okay, let's remove this 4. Okay. So 1, 2, 2, 4 times 4 times 1. So that's R2 equals R2 minus 4 times R1. And then I'll do, so that will be 0. 5 minus 4 2s are 8. So minus 3. And this will be 3 minus 4 times 2 is 8 again. So that's minus 5. Right? And so this will be 3, 3, 3. Okay, great. So let's remove this 3. Oh, okay. Before removing this, we can actually remove this 3 now. Okay. So now what we'll do is R3 minus R3 equals R3 minus 3 times R1. So I want to remove this 3 by multiplying 1 with 3. Okay. So what do you get? 1, 2, 2, 0 minus 3 minus 5. 3 times 1, 3 times 1 is 0, 3 minus 3 is 0. Okay. So I got 0. Now 3 minus 2 times 3 is 3, minus 3. Okay, great. Now 3 minus 2 times 3 again is minus 3. This is correct, right? 3 minus 2, yeah, this is correct. So then what I'll do is I will remove this 3. Okay, actually what is better, yeah, and it's equivalent. Okay, so I'll do R3 equals R3 plus R2. Okay, so that way I'll add these two. Oh no, minus R2. That way I'll add these two. 1 2 2 0 0, and here I get a minus 3, and here I get a 0, and here I get minus 3 minus 5 will be plus 2. Okay, and here I get a minus 5. Okay, great. Now what can I do further? Well, I can remove this 2. Okay, if it helps, let's do that. Okay, is equal to 1 2.
But
Yeah,
but then Gaussian elimination we used to form a stair like structure, and so
that is
I
true.
mean,
That is true. That is true. So what I'm trying to do is I'm simplifying it. It's the upper part of the stair can be anything. So even if I set those two zeros, that's okay.
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 uh, there was a difference in between the Gaussian elimination and Gauss-Jordan one, wherein in the Jordan one you make other things as zero as well, if I remember.
Yeah,
Or
yeah,
there was
yeah,
some.
yeah. You'll basically what you'll do is at the end you'll add this 1 0 0 0 1 0 and so on. But that is like if you want to solve it directly. What we just want to test for linear independence and so on.
Okay.
So that would not be a problem. I think I made a mistake. This looks like this is full rank. What did I do? I set this to 2, no? Okay, that should have been 0. Yeah, this. If I continue trying to do this will be full rank. This part should have been 0 because, yeah, this should have been 0. Sorry. Okay. Is it depending on R1? Yes, it is depending on R1. Minus 4 times R0, so that will remain to become 3, and minus 3 times R1. So this will be 0 and this will be 3. And so now R3 minus R2. 3 minus R2 is 3 minus R2 is 8. Okay. 3 minus R2. Yeah, that will be 8. Okay, but still I don't see a clean shot at it. Okay, let's still try. 1. So I want to remove something from here. So I need to do something like, oh, it'll go ugly now because I'll multiply by minus 1 by 3 here, and then go minus 1 by 3. Okay. So 2 minus something, 2 by 3 times minus 3, meaning that I'll do 2 plus. So I need to do row 1 plus 2 by 3 times R2. So that will be 1 minus 0 is 0, and this finally will be 0, and 2 minus 5 8. Okay, there is something wrong here. Well, this is clearly linearly dependent. See, because I mean that is because I know the dependence already. So the dependence would be that column 1 times 2 plus minus column 2 equals column 3, right? So 2 times 2 times column 1 is 1. 1 times 2 minus column 2, that's 2 is 0. And 4 times 2, which is 8, minus 5 is 3. And 3 times 2 minus 3 is equal to 3. So this is clearly linearly dependent. These 3 columns actually depend on each other. But somewhere I've made a mistake. Okay, I'll think about it. But I don't want to slow down the class. Okay. Anyhow, okay. Yeah.
This value is not correct. I mean, -5 is not correct. Because minus 5 is not correct because 3 minus 4 times 0. So the value will came out to be 3.
3, yes, that is it. Yes. 3. The rest is fine, no? 3 minus so this will be 3. This is correct. Yeah. Now it's working out. Thanks a lot. So now you can easily see that these two columns have become linearly dependent. Now all you need to do is R3 equals R3 minus R2, and this entire thing will become 0. And this will remain 3.
So what used to be the pivot elements here?
What used to be the pivot element? Okay, now pivot element is, you can interpret it in two ways: in reduced row echelon form until you go till 0, 1, 1, 0 and so on, or you can even okay. See, you see that I can always trivially make this 1. No, if there are zeros to the left, I can always trivially make it 1. I'll just multiply. I'll just do R2 minus something like 3 by 2, R2 plus 3 by 2, and make this 1. You see, that's just the next step to make this 1. So the complete Gauss-Jordan algorithm would say R2. Okay, in R2, what do? You do R2 plus whatever is here, you put it. Whatever is here, you put it in the denominator. Okay, 1 by 2. Okay, and whatever is here, you put it in the numerator. Okay, with the sign changed, or you can put minus here. Okay, R2 minus, put whatever is there in the numerator, times R1. So when you multiply this minus 3 by 2 with this guy, and this minus will cause a plus 3 to happen, and these two will cancel out. No, and then you can easily get rid of that. But the main point is that when you get that final staircase form, okay, either this or even this will become 0 and so on. Okay, finally, when you get the staircase form, these elements are what are called your pivot elements. So each of the step in the staircase, okay, are called your pivot elements. Now you see that here there is a problem already, because in here there is no third pivot element, because a pivot needs to be non-zero. Okay, so you have 1, you have minus 3, and the third pivot is missing. So let's say this has 2 pivots. So the rank is 2, which means it is not full rank, which means that there are linearly dependent vectors here. Okay. Now, but what does pivot actually indicate? What does pivot actually indicate? If there are 2 pivots, it means that there are 2. I'm being a bit hand wavy, but I'm saying 2 linearly independent vectors. I'm being a bit hand wavy. Later on, when vector space comes, I'll talk about it. But it somewhat means that there are only 2 linearly independent vectors. If there are 3 pivot, it means all 3 are linearly independent. And if there is only one pivot, it means there is only one linearly independent vector in that space. Okay, I'm being a bit hand wavy. Okay, but what it actually means is, if you look at the space, vector space that it's spanned by these three, then the basis will have two vectors, or the basis will have three vectors, or the basis will have one vector. But for now, you can imagine it to say something like, two of the vectors are linearly independent, or three of the vectors are linearly independent. Okay, although this is not entirely correct. Yeah, Kishore.
See, this Gaussian elimination only defined for linear to know the pivot values and then to express in a linearly dependent, right?
Yeah.
Not for the linearly dependent.
So if you look at the total number of columns, okay, the total number of columns, okay, will be equal to number of linearly independent columns plus number of linearly dependent columns, or equivalently number of rows in a square matrix. I'm saying number of rows is equal to number of linearly independent rows plus number of linearly dependent rows. It's either one or the other. So if Gauss-Jordan tells you number of linearly independent rows, it will tell you number of linearly dependent rows also, because you know the number of rows equivalently for columns.
Okay, so subtracting from total number of rows linearly dependent, we will get the linearly dependent.
You will get the dependent.
That's the logic, right?
Yeah, that's the logic.
So, but see, when you go back to the previous slide, so we got eventually we got the solution after Gaussian elimination. One first place in first row, and then second place one we got in the third row we got all zeros.
In the third row we got all zeros
after completion of Gaussian elimination. We got a matrix, right?
One moment, sorry.
Slightly below in the slide, yeah.
Below.
Below.
Okay.
Still below. Yeah.
Yeah.
This one, right? So see, by this what we know is there are two linearly independent and one linearly dependent. Is that mean when we say there if all the three vectors are linearly dependent, is that mean after Gaussian elimination? I'm not sure, but doing Gaussian elimination, do we get all zeros?
No, you get one non-zero. Okay, let's test that out.
One non-zero.
Yeah. Okay. Let's test that out. Okay. Let's test that out. So clearly, 1, 2, 3, and 2, 4, 6, and 3. Okay, 2 to the 4. Okay, 4, 8, 12. This is there are like so many linear dependence. No, it's very linear dependent, because see, if you look at column 1, okay, if you look at column 1 is a 2 times column. Sorry, if you look at column 2, it's 2 times column 1. If you look at column 3, it is 4 times column 1, or equivalently it is 2 times column 2. You see it, no? You sure?
Yeah.
Now, if you apply Gaussian, by the way, Gaussian elimination you can apply on the columns also. Okay. Let's say I apply.
One second. See, based on the C3 is equal to 4C1 is equal to 2C2. So based on that, can we say based on this itself, so all three vectors are linearly dependent?
Exactly. All three vectors are linearly dependent.
Yeah.
No. Okay. Now I'm coming. Yeah. Sorry, I forgot to mention that all three we can clearly see all three vectors are linearly dependent. Now what I want to say is that when you do Gaussian elimination, you'll end up with one single column. Okay, so if you do now, it is the trivial thing to do would be take C3, and from C3 you remove 2 times C2. What do you get? You get 1, 2, 3, 2, 4, 6, and C3, 4 minus 2 times 2 is 0, 8 minus 2 times 4 is 0, 12 minus 2 times 6 is 0. Okay, you get this. Now you apply Gaussian elimination again on the columns. So what you'll do is you'll do C2 is equal to C2 minus 2C1, and then you get 1, 0, 0, 2. No, again 4 to the 0. Sorry, 2 to the 4. So,
I think C3 is equal to C3 minus 2C2. If we do this for the first element, let us suppose the first element in the first row should be 2 into 2, 4, minus 3. Oh, minus 1 it gets. Minus 1 we get, right? Here.
2 into 2, 4.
Because C2, 2 into 2 C2.
Which one? This part or this part?
Oh, it's a column. It's a column, right? Oh,
Yeah, it's a column. Yeah. Okay. You can see that there's only one column left. Now, no matter how I do Gaussian elimination here, I'm going to get 1, 2, 3 only. If I add, column, subtract, whatever, I can get like minus 1, 2, 3, but that is the most I can get. So you see, right, if all 3 of the columns are linearly dependent, okay, then you will get one column vector. See, I can explain why you get one column vector also, but we've not done vector spaces. But if you still want more exposition, just let me
know. No, so if we have in further classes, if we have expression about this, of course, I think we can continue with the today's topic.
Oh, okay. Yeah. So even if I don't explain, I won't introduce vector spaces. Just remember that there are. It's about if you have. In this case, it's 3-dimensional. If you have a 3-dimensional surface, okay, and a vector space represents using your combination of vectors. Where can you travel to on the space? Okay, and since all 3 of these vectors are linearly dependent, 1, 2, 3 will be something like this, 2, 4, 6 will be like this, and 4, 8, 12 will be like this. Okay, what Gaussian elimination will do will be remove all those which are duplicates of each other, all those vectors. Okay, so if there was another here, okay, and another here, so it will remove this duplicate. Or even if, like, let's say there is another vector here, okay, which belong to the matrix, okay, so these 3 were, let's say, in the matrix, okay, and if it so happens that this is a resultant of blue and green, red is a resultant of blue and green, which means this is a linear combination. Gaussian elimination will make sure that this is removed. Because it is a linear combination, this exactly represents a linear dependence, linearly dependent. Okay, so Gaussian elimination will remove them. Now what you are saying is, look at the matrix now. Your matrix will look somewhat like this when the vectors are plotted, right? Gaussian elimination will remove all the duplicates, and then you'll get one vector, okay, which, I mean, if you reduce it to its simplest form, is what is called a basis vector, and it represents where all you can travel. You can only travel through this line, and that's it. That is what the reduced or row echelon matrix actually represents. It represents like the base, it gives you a good idea of which areas you can travel. For example, if your matrix had become 1 0 0 0 0 1 0 and then all zeros, okay, you can see that what is the rank here? Rank is 2, and it has 2 pivot elements. Okay, it has two pivotal elements, meaning on this dimension, z dimension, those vectors cannot travel at all. Okay, at least, or in other words, in one dimensional they cannot travel, which means that these they can travel only on a plane, and that's it. They cannot go outside the plane. But if it so happens that 1 0 0 0 1 0 0 0 1, this happens. So what is the rank here? Rank is 3. This set of vectors can travel everywhere across R3, anywhere in R3. Okay, it can travel wherever it wants in R3, and this set of vectors is set to span R3. For example, this can only travel in a plane, so this is set to span R2. Not 3 shouldn't be below, what I mean. Okay, something like that. Yeah, Kishore.
See, for the set which has rank 2, right?
Huh.
Of course, what we understand is z vector will not travel. Only the chance of only x and y vectors have the chance to travel, right? So, how to identify whether they travel in a same direction or different direction within the plane? Is it something it itself indicates it will travel in the same direction within the plane, or there is something which indicates
So finding that plane, okay, using Gauss-Jordan, I mean, where it can travel within Gauss-Jordan, that would not be possible with Gauss-Jordan. So you'll need to you'll need to analyze the vectors and then understand, because the valid set of x and y could be anything.
Okay, just we can find out the magnitude itself, not the direction.
You that too, okay, but you can actually do it using other things. Okay, for example, all you need to do is actually find what are the basis vectors and find the plane where both of them lie. If you do that, then you're done, because any combination of these two vectors will always lie on the same plane. Okay, and the third vector is anyway linearly dependent, so its effect will also be on the same plane. That is the concept. Okay, yeah. Okay, good. Okay, so I hope that clears it. Now, okay, and then there's this third one. Again, you can try it. Okay, this is also linearly dependent. You can apply Gauss-Jordan and find it out. Okay. Now, okay, let's look at the main content of this this time, which is cross product. Okay. Oops. Yeah. Okay. Okay, here you go. So look at this question. Try to answer it. So cross product of two vectors. Hi. Yes. Hi, Mr. Shivkumar.
A cross product of two vectors is always a vector and perpendicular to the plane of those two vectors which we are doing cross product.
Yes, correct.
That is-
Okay. Okay. Yeah. It is a vector, so that means it cannot be a scalar, right? So what about C and D? So is it
So cross product would mean the what? The outer product or what? Outer product. So like say
Yeah,
the cross product would mean say the you and I take the transpose of V, that kind of a thing, and that will result into the cross product. Because we have inner product as well, and that would mean say I take the transpose of U and then I take the product with V.
So okay. So I mean, there is a particular formula to cross product, Koel. So so I mean, there are quite a few formulas, but this is one way to do it. Okay, and this is the cross product U1. Now it's not the formula that is important. Okay, it's more important what it philosophically represents, or at least geometrically represents. Okay.
So like say if U is a vector,
Huh.
and which has got say 3 components. So if I take the products of U and V,
Huh.
so
Huh.
say the dimension of U would be 3 into 1. And if I take the transpose of V,
Huh.
so that would be 1 into 3. Like say for U you can write say U1, U2, U2 and U3 say column wise.
Huh. 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 Huh.
And I take the transpose of V, so convert it into a row vector and say it is V1, V2 and V3.
Mhm.
And now I take the product, and this will result into what? A complete matrix of the dimensions say 3 cross 3.
Hmm.
And so
Oh,
what that product
I mean,
is this a cross product or something else?
so I didn't completely understand.
So can you write this U vector as a column vector, say U1, U2 and U3?
Column vector u1, u2, u3. Oh, okay. By the way, I forgot to. I mean, there should be some kind of normal vector here. Okay. Otherwise, it will be a scalar. Yeah. um,
And this vector V as a row vector V1, V2 and V3, and now you take the product as we do in the normal
yeah. Okay. I mean, maybe that would be one way to say it, but
Is it same
see,
as when we say cross product, right? Is it same as matrix cross product, or it's different?
no, it's different. Cross product between vectors is different. Okay. See, I'll tell you exactly what it is. Okay. Okay. So the idea of a cross product comes from the following. Okay, a cross product represents, okay, between u and v represents a vector, okay, which is, okay, it is important. It's a vector. It's not a scalar. Okay, it represents a vector which is orthogonal to both u and v. Okay, so now what does that even mean? If you have in 3 dimensions one vector here, let's say, another vector here. Okay, great. I want a vector which is perpendicular to both of these guys. You get it? So how do you do that? So if you want to visualize it, it's like, see, this is a vector, okay, and this vector is somewhat like this. Okay, I want something. I want another vector. Okay, or let's do something like this. I want another vector which is perpendicular to both. Well, you can always like put like another vector which goes through both of them like this, right? So that is what cross product represents. Okay, it represents a vector which is perpendicular to both of them. Okay, which is perpendicular to both of them. That is cross product. But the cross product, um, so I mean it also it is not just that. Okay, it's so it also has a magnitude. No, okay, direction definitely is perpendicular, but a vector has a magnitude also. So what is the magnitude of the cross product? So the magnitude is surprisingly equal to the area of the parallelogram. Okay, area of the parallelogram formed by the red vector and the blue vector, which is, let's say, u and v. This is u, this is v. Okay, and here you have u cross product v. See, the best example I can give you of a cross product. It's been a long time since I've done physics, okay, but in high school physics, you had this electromagnetic equation, no? What?
Yeah, I remember that used to be to compute the flux, and we used to use our hands, two fingers, and then one thumb. And B
Exactly,
is equal, B is equal, B is equal to mu naught upon 4 pi I dl cross R, and then divided by the
yeah,
R
what
cube.
was that? B equals?
B is equal to mu naught upon 4 pi. Mu
Mu,
naught,
okay.
mu naught
Okay, mu
upon
naught.
4 pi,
4
upon
pi.
4 pi, and in the numerator I
Okay.
is a I, and then multiplied by dl cross R, the
Okay.
cross product of dl and then R, dl vector and then R vector.
Oh, okay.
Both are vector, yeah, and divided by R should be small. I remember in the formula this used to be small.
Okay.
To know the direction of the flux, I remember, and divided by R cube. Yes, R cube.
Capital or small?
Divided by small R cube.
Okay.
If we change the upper one into a unit vector, then the denominator used to become R square, I guess.
Okay.
This
Okay.
used to-
Okay. 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 Yeah. I mean, yeah, it's been a long time, but yeah, since
Long time.
but yeah, I need to comment your memory, well. uh, yeah. Okay. I would not have been able to remember, but either ways, I think yeah. I think so. What it had three components: the electromagnetic field. Okay, it had the current, and the other was a force, right? So it always said that okay, if there is an electromagnetic field in one direction and current in the other direction, where is the force going? Then there was the right hand rule and the left hand rule. Remember?
Thumb direction.
Thumb direction.
Direction
Yes.
of the thumb.
The direction of the thumb. So, but I forgot which order the index finger and the middle finger were. One of them was current, one of them was the magnetic.
Index is always field,
Index is
and
field.
middle finger is always the current.
Current. Okay. Middle finger is thank you. Middle finger is always the current, and this will be the force, right? If you remember, why was the cross product there? Why was the cross product there? Because the cross product does not just represent the force; it also represents the direction. We can easily say that okay, the thumb is the to get a sense of it. But on paper, if we want to not lose the sense of direction, we have the magnitude, but we also want the direction. That's why this cross product was there, and we used to replace it with this instead of dlr, we used to replace it with sine theta, right? Because that is exactly the formula for the cross product. Okay, now, oh, it's called Biot-Savart's law. Okay. Oh yeah, I am recalling now. Good to recall. Yes. Okay. And this right hand rule is applicable here also. Okay, the right hand rule is applicable here also. And why is it applicable here? Because it depends on how you are measuring theta. Okay, so I'll tell you. If you remember, if I have two vectors, okay, I have a vector, let's say like this, and I have another vector like this, okay, and this vector is 2 2, and this vector is what 1 2 3 4 5 5 2. Okay, now tell me the area of the parallelogram. This is 2D.
So
It's base into
that
height.
should be the determinant of this.
Okay, so it is determinant of 2 2 5 2. Right, good. 2 to 5.
Can we also go with the what do you say, the base into height formula?
Okay, base into height formula is there, but I'm asking in the vector context.
Okay.
So this is correct. Okay. So let's do let's multiply. So what do I have? 2 times 2 is 4, minus 2 times 5 is 10. So 4 minus 10, which is minus 6 square units. Right. Okay. This is correct, no? But let's say I do the other way around, which is okay, which is that if I look at this 5 2 vector first, okay, if I look at 5 2 vector first and then look at the 2 2 vector, okay, then look at the 2 2 vector, okay, and consider the parallelogram with it. I'm getting two different answers, because then what I get is I get 5 2 2 2 and one moment, sorry. Sorry. Hello? Amazon? Package, where are you? Oh, cycle shop. Okay. I'll collect tomorrow. I'll collect tomorrow. Okay. Array, can you lock my cycle? Can you lock my cycle outside? I'll send. Yeah, number lock. Number lock. Password is 1024. Phone pay. Okay. Okay. How much? 330. 330. Okay. I'll send immediately. Phone pay. Okay. Okay, phone pay or Paytm. Okay, I'll do Paytm. Okay, thank you. Hello. Yeah, hi. Very sorry for the interruption. Yeah, Mr. Shivkumar, you were raising your hand.
I'm in the meeting now. I'm listening to your lecture.
Oh, okay. Yeah. Sorry, I had an interruption in between. Sorry. Okay. So if you do 5 to 2, okay, and then do a determinant with this. 5 2s are 10 and 2 2s are 4. Then you get minus 4, which will give you 6 units, square units. You get it, right? So why is this happening? That's very strange. Why is there a minus here and there is no minus here? Okay, so determinant represents the area of the parallelogram, but it's also doing something extra with this extra sign. So this minus and plus here. This represents what is called the orientation. Okay, of the resultant. But I won't get into the orientation of the resultant. I want to get into the orientation of the dot cross product here. Okay, orientation of the cross product. The idea here is, okay, the idea here is that you have this. I'll copy this diagram. Hello. Hello. So where are you? Computer science block. Okay. 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 I'll send someone. Okay. Hi. I just need to leave for 2 minutes. Okay. I'll be back. Okay. Yeah. Until then, please think about the problem. Okay. I'm really sorry. Yeah. Just give me 2 minutes. Thank you. Hi. Sorry. Yeah. I'm back. Okay. Yeah. So, yeah, where was I? Okay. Yeah. Yeah. Okay, sure.
Yeah, see, basically, what I understand is orientation with respect to a vector is it's a direction exactly. See, let us suppose.
Exactly.
See, it's let us suppose positive sign indicates on a vector system towards the positive axis, and when we say in a negative sign, it moves in a opposite direction.
Right. 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 That's right. That's right.
That's what my understanding is.
Exactly, exactly. Because now you consider this, right? So look at this diagram. So V is pointing here and U is pointing here. Now you ask, what is U cross V? Okay, you ask. And you'll say, oh, okay, this is a perpendicular, so this must be it. But then you may also ask the question like, why not in the opposite direction? Because there are two perpendiculars, right? Technically, one in the one in the direction going left, and the other in the direction going right, or equivalently going up and going down. Which one? Now that's why we say the right hand rule, right? Do use the right hand rule, okay, and then you figure it out whether it is this or whether it is this. But why does the right hand rule work? Because it matters how you measure theta. Okay, how you measure theta, because of the fact that are you measuring theta this way or are you measuring theta this way? Okay, and for one of them sine theta will be positive, and for one of them sine theta will be negative. Okay, and the fact that you have a sign in the formula will actually dictate that. So when you do the cross product of U cross V, everything remains the same. Okay, everything remains the same. The magnitude is same. Is the same as V cross U, except the sign gets changed. Okay, so that would mean that it is not commutative. So U cross V is not equal to V cross U, but it is commutative. Commutative up to sign change. Okay, so this is one property of cross product. Okay, sure.
See, of course, based on the explanation, I agree that it's not commutative. But see, when we are calculating the angle of the same degree, but in a different direction, it lies in the same plane of a coordinate system, right?
When you
see, you said that the sine theta will be negative when we calculate in a other direction of the theta.
Yeah.
And then if we go from bottom to top, it will be positive sign.
Yeah, that's right.
So that angle, right, that theta angle, it lies in the first quadrant of the coordinate system.
That is a bit different from what I was mentioning. Sorry. See.
So where is the trick it is happening?
Exactly. Sorry. So what I meant was, see, this is a vector in a 2D system. Okay. This is what is a positive theta, and this is a negative theta. That is what I mean. Nothing about quadrant so far.
Yeah, but I understand this. That was my my question was.
Yeah.
See, though you calculate the angle from top to bottom or bottom to top, it is the same angle, right? So where is this trick happening?
The trick is happening whether in the interest of which one is U, which one is V. You get it? Which one is U, which one is V? Because, okay, where is the trick happening exactly? I'll tell you. Because when you finally get the parallelogram, okay, there could be two types of parallelogram depending on the kind of U and V you are taking. One of the parallelogram will have shorter side here and longer side here. Okay, and the other parallelogram will have the same dimension, but it will have longer side here and shorter side here. This is what orientation means. The area is the same, but it's mirror images of each other. So one will have a positive sign, one will have a negative sign, because it depends on which one is on the left. If U is on the left, V is on the right, it is positive. If V is on the left and u is on the right, and still you're calculating u plus v, then it is negative. So that is where the trick is happening, Kishore. Okay, so that is where it's happening. Okay, you can check out orientation. Okay, I don't think much focus is done in the course, but this is what is internally happening. So the final one. Okay, you may not know the answer to this. Is possible in any number of dimensions. Think about it. Okay, let's ask a simple. Yeah, Kishore.
Is it dimensions in the sense the size of the magnitude it means?
No. Dimensions as in, is it, I mean, in 1D, 2D, 3D, 4D, whatever.
Okay.
So think the fact that why did we wait until 3D was introduced in the course to talk about cross product? Okay.
Possibly it happens only in 3D.
Okay.
That's the reason we haven't spoken or discussed that in 1, 2, or 2.
Yeah, Mr. Shivkumar.
This cross product is product of two vectors whose magnitude we know, and the direction of the vector is perpendicular to the plane of these two vectors.
Right.
Now, when you say more number of dimensions, you mean u is u1, u2, u3 like that. U3, U4, and v is v1, v2, v3, v4. Like that.
Right.
That means that you are calling it as multi-dimension.
That's right.
So in that case, the cross product will be, is it like u1 cross v1, u2 cross v2, u3 cross v3 like that?
Yeah. So no, not exactly. We mean that again the same definition, that if there are, let's say, 4 dimensions, can I always say that if given two vectors that lie on the same plane, can I find a perpendicular to the plane that the two vectors lie in 4 dimensions? But
it's difficult to imagine for me also.
It is difficult to imagine. I mean, I gave this question as a fact. I do not have a proof for this. So
What I thought was,
if
you say u1, u2, u3, they are the components of the vector.
That's
like
right.
ijk.
That's right. Yeah.
So each ijk has this thing, what do you call, I cross j if you take, it will be k.
Yeah.
So in that sense, for a 3-dimensional vector, you have a vector product which can be found out. And it is possible. Two such vectors if you take, and the components are known in a Cartesian coordinate, you can find the cross product.
Right. But well, it so happens that I do not have the proof for this. Probably the proof is very complicated. I just gave it as a fact, just for general knowledge sake. So it turns out that you cannot have cross products, or rather it is not known that you can have cross products besides number of dimensions 3 and number of dimensions 7. In fact, between 3 and 7 you cannot find cross product, and below 3 also you cannot. I mean, it's not possible to always find cross product. So it's not well defined, in fact. There. Yeah, Kishore.
What my intuition says is, of course, the magnitude remains same irrespective of the dimensions of the both vectors.
Magnitude remains same. Okay.
Yeah, and when we see in one-dimensional, we can able to see both vectors, and also as well as 2, 3, 4, 7 as on. In fact, in few of the dimensions we can't able to see those vectors on the plane, but for few of the dimensions we can see them.
Yeah.
So as per the question, right, is it possible to any number of dimensions? Of course it is, but not all of the dimensions.
Yeah.
It is my intuition.
So it is so it's something that I do not have an explanation for as of yet because I was just curious
Because
and I
why
looked it
I'm
up. Yeah.
because why I'm saying this is
Hmm.
when we were trying to uh, give the output of some of our AML, what do you say, the plotting.
Hmm.
So we see in the 3 dimensions as well as in 2 dimensions, and then of
Hmm.
course single dimension. That's okay.
Hmm.
So what I found is, of course, I haven't seen them on 4
Hmm.
more on.
Hmm.
So when we see an object after plotting in
Hmm.
changing dimensions,
Hmm.
it sometimes what happens is it changes the orientation. That's sure.
Hmm.
And
Hmm.
sometimes in few of the plotting, so what I've seen is in 2 dimensions I've seen the object, but when I go to 3 dimension, the object will not be visible.
The object will not be visible. Okay.
Right. That means when we look at from the 3rd dimension, right?
Huh.
So it won't. We can't see that object. When we come back to the 2nd dimension, of course we can see the dimension that object.
Hmm. Hmm. Hmm.
So that's where my intuition says this. Maybe I'm not sure about that.
Yeah, I mean that could be a correct intuition to go through. It makes sense why below 3 you cannot have a concept of cross product because of course um, in 2 dimensions you only have two vectors. Third vector
Exactly.
perpendicular does not make sense, and
Yeah.
in 1 dimension you can just have one vector in
So
either
even in
directions.
that case as well, if we go on from starting from 3, 4, and so on.
Yeah.
Okay. So if we just rotate the coordinate plane,
Hmm.
we could able to see that. Of course, we have some online what do you say these plotting softwares.
Hmm.
So once we plot them, and then we can orient the dimensions, right? Sometimes to if we wanted to see in a 4th dimension, right?
Hmm.
If we see them, then it sometimes that object will not be visible based on the plotting. For some plottings, it will be visible, and so on
Yeah.
for face.
Yeah. I mean, it's hard to actually plot for. Yeah, it's still possible. For example, like you have these, color plots. I mean, you coloring in plots, and you can add a fourth dimension there, but it won't actually represent visually what fourth dimension looks like. But yeah, interesting. Good. Yeah. Well, I'll look into why this is true. I just was curious and I googled it up. Okay, I just gave it as a question here, but I don't have a solid answer why this is true. But it is true that until as of now, it's only clear that cross product can only be defined on 3 dimensions or 7 dimensions. Okay. Um, okay. So I mean, those are some of the properties of cross product. So here we have. Okay. Another problem. So here you have it. Now, oh, okay, it has so many things. Okay. Okay. So before this, I just want to give you the formula of cross product. So the general formula of a cross product, if you have two vectors u and v, okay, and u is u1, u2, u3, and v is v1, v2, v3, and check out the lectures to see the proof of this. Is cross product is u2 v3 minus v3 u2, u3 v1 minus u1 v3, and u1 v2 minus u2 v1. Okay, so this is the formula for cross product. Of course, you can have the sine formula also, but then of course you need to calculate theta and so on. So now it's just a direct application of that. Okay. So it's the question is saying find the vector orthogonal to both 1, 3, 1 and 2, 4, 1. Okay. So let's try A. V1 equals 1, 3, 1 and V2 equals 2, 4, 1. And what you want to do is cross product between V1 and V2, okay, which is nothing but 2, 3, 3, 1, 1, 2. 2, 3, 3, 1. That's not called V1, V2. U1, U, V. Okay. 2, 3, 3, 1, 1, 2. Minus V2, 3. Okay, that doesn't make sense. This is supposed to be UV, sorry. UV. That makes sense. So you just do U3 V2, U1 V3, U2 V1. Okay, and so that will be. So let's just map it out. U1 is 1, U2 is 3, U3 is 1, V1 is 2, V2 is 4, V3 is 1. Okay. So it's just 2 times 3, 3 times 1 minus U3 V2. So 2 U3 V1 2 minus U1 V3, which is 1, and U1 V2, which is 4, minus U2 V1.
So what this V1 cross V2 here is?
Yeah.
V1 cross V2 here is. What is that?
Exactly. So this is a vector orthogonal to both V1, V2, where I'm measuring the angle from V1 to V2. Okay.
But then what are V1 and V2 here? We have been given U and V.
Sorry. Yeah, I forgot to replace this. Yeah.
Okay.
UV.
UV, right. So then, is this a standard formula to compute the cross product?
It is. Okay. It is a standard formula. You can memorize this, or there are some tricks to actually do this. You arrange it into 1, 1, 1, and or rather it's like you arrange it into these unit vectors, although it doesn't make sense to put vectors within a matrix, but bear with me. You put this and then you put u1 u2 u3 v1 v2 v3, okay, and find its determinant. If you find its determinant, then you'll get this formula. Okay, in a sense that yeah,
I believe this formula is just for 3 dimensions, right?
Yeah, but we said no, that the cross product anyway you can't do it in more dimensions.
Yeah. Just a confirmation I'm asking.
Yeah.
This is up to limited to 3 dimensions.
3 dimensions. Yeah. This is just a trick, okay? This is just a trick where it may or may not have actual connections. Okay. But because this formula is actually derived from a very different way. So, but when you find its the determinant will be, you take I out, and u2 v3 minus v2 u3 minus uh, and then you do u1 v3j minus v2k, and then group all the j k together and so on, and then finally you will get this formula as a vector. Okay. Anyway, see, this is the answer. This is the vector which is perpendicular to both u and v. Okay. Now, now the question says b. So try b. A is done. So you have 3 1 2 2 4 1. Okay. Now you do so u1 is 3, u2 is 1, u3 is 2, v1 is 2, v2 is 4, v3 is 1. Okay. Now you find the cross product 2 3 3 1 1 2. So it's better to memorize it. So you remember 2 3s, 3 1 and 1 2, and then all you need to do is put minus signs and exchange the u1, v2 u3, okay, v3 u1 and v1 u2. Okay, so what do you get? You get u2 v3 is 1,
10 minus 7 minus 1.
10 minus 7 minus 1. Okay, let's see. v2 u3, v2 u3 is 2. You got 10 in the first entry.
So what I took is first u1 v2, and then that's how it's
u1 v2. Oh, you mean you are saying from the bottom?
yeah.
Okay.
I mean, like, so the calculation what I took is v1. Okay, let me rearrange it and tell you.
Okay. v3 u1 is 3, u1 v2 is 12, and v1 u2 is 2. Okay.
Yeah, it's same. Minus 7 minus 1 10.
Minus 1. Okay, I got 1. 3 1 u3 times 1 2 to the 4 minus, yeah, it should be 1, no, not minus 1. No,
It's what is that? It's v3 v2 v2 v4 minus
minus 7 1 10 is correct.
Yeah.
Yeah, that then is correct. It's only the sign for second element.
Okay. So okay. So and the final one. See. So is there a faster way to do C? Hmm? So well, in order to do C, all you can do is that it is just the opposite of B, right?
So answer is for the third one
Yeah,
is
what?
7 minus 10.
Exactly. So yeah, good. So this is just reverse of this. So if this was U cross V, this is V cross U. And we know that the cross product will be equal to the negative of the original cross product if you reverse it. Okay, if you reverse the okay, if you reverse the order. So this means that for part C, you just apply minus 7, 1, 10, which is equal to 7 minus 1. Okay. So yeah, there you have it. It just means it's in the opposite direction. Uh, Now let's do this one. Okay, so this is fine. I mean, see if you look at question 4. Uh, okay, if you look at question 4, it is quite simple, right? What will you do in question 4? We don't need to solve it. Just tell me. Start. Okay, I'll just look at question 4 and 5. Okay, I need to get my charger. Sorry. Okay. Yeah. Okay. So how do you do 4? Yeah. Sometimes. Yeah,
Some
right.
time back
So
you have
see,
discussed on this.
um,
Just some time
so
back, I think we have discussed on this, the aerial parallelogram.
anyway, the first one is anyway two-dimensional. Okay. Oops. See, the first one is anyway two-dimensional, so I can always represent it as a matrix. And then do what? I'll just compute the determinant. I'll just compute the determinant. And I'll just get 2 minus of 5 times 3 is 15, which is equal to minus 13. So area is equal to 13 units, square units. Okay. This I can always do. But what is the problem? Can I do the same with B? Can I do the same? Yeah. 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 Exactly. Yeah. Exactly. But why can't I do the
We
same
have
technique?
to take
Determinant.
We can
cross
prove it.
product. B, we have to take cross product and take the magnitude.
No, but I can't do determinant of this.
You are in a way doing determinant only here.
Right. So yeah. If I add IJK, I can do determinants. That's right.
Of non-square
If
thing,
if
you
I add
cannot
IJK, I
complete a
can do
determinant.
determinant. That's right.
IJK,
But
unit vector is
otherwise, like you said,
yeah.
we can do a cross product. So cross product will anyway represent the area of the parallelogram. So along with the direction. So all we need to do is 682 cross 231, and then use the formula, and we'll get some answer. Okay. Okay. So this I think you can practice, but let's move on to some other more interesting questions. Okay. So, so let's look at 5. Okay. Let's look at 5. Okay. Crop it. Done. Okay. So let's look at this. So can you think about this? How to do this? It's not too complicated. I mean, it's quite simple. So you have a 3D vector, which is 312, and you want its projection. By projection, I mean orthogonal projection. If it's not mentioned, then it is orthogonal projection. Okay, of the vector on the xy plane. So the plane formed by x and y axis. Right? Huh?
So on the xy plane, z is equal to 0. So you take
Exactly.
the vector projection on xy plane with z is 0. So 3, 1,
Exactly.
0.
You actually you don't even need the cross
vector
product
on the xy plane.
because
Take cross product
okay,
of
if you
those
want the
two
vector, yeah, you need
you
the
will
cross
get.
product. Correct, correct.
I hope so.
But if you just want the point, then that's all. So what you have is say 3 and say 1, okay, and or rather, let's say this is 3 and this is 1 and 2. So let's say this is y, this is x, this is z. So you have x. Which one is x? So all you have is 1, 2, 3, and then you have 1 on y-axis. Okay, so y-axis is here and 2. Okay, so that's your vector. Now, what is your plane? This is your plane, xy plane, formed by x and y. Okay, and what is the what are you saying? Well, you are projecting it below on the xy plane. So basically, what you are saying is you are somewhat like shining a sun on top of it, and then seeing where it will fall. And you already know that with respect to x, it is 3 units, and with respect to y, it is 1 unit, and z is anyway. I mean, it's two units above the plane, above the xy plane, because xy plane is at z equals 0. Anyway, you don't need this, so this is redundant. So where does it fall below? It falls on 3, 1, 0. Okay, and that is enough. You're setting z equals 0. So I mean that would be one particular way to see it. But this is like a very simple question. It's like saying if you look at 2 dimension, it's like saying you have an xy, you have a vector like this, and you are saying what is its projection. Okay, and this vector is, let's say, 3, 4, 5. Let's say this vector is 4, 5. It's like saying what is its projection on the y axis, and then you just drop here. Anyway, 5 is redundant because now you're only seeing on the y axis, so you'll just consider 4. Okay, but now we can do something more interesting. Okay, and here's the question. Okay, and so this was done in the lectures. I mean, not the question, but the concept. So that is projecting a vector on a plane. Okay, on not any kind of plane, a plane which passes through the origin. Okay. So the question says, given a vector v 104, project v onto a plane x minus 4y plus 2z equals 0. Okay. Now, just one moment. Okay. So all you have is this axis. Okay, and you are saying you have this vector 104, and you have this plane x minus 4y 2z. Okay, let's just, we don't need to make the vectors accurately. Let's say this is 104. Okay, this is v. Okay, now there is a plane. Okay, there's a plane, and there's a plane which looks like this. Okay. Oh, okay. This looks too let's say, huh. So this is a plane. Okay, yeah. Now the question is, you want to find, and this plane is x minus 4y plus 2z equals 0. First of all, you can see that it needs to pass through the origin because it is a homogeneous equation. And if it is a homogeneous equation, one of its solution will definitely be 0, 0, 0. X equals 0, y equals 0, and z equals 0, which is called the trivial solution of the homogeneous equation, which means it will always pass through the origin. Now what you are saying is, you have V, you want to project it on this plane. Locate that point. Okay? Locate that point. Well, question is like, first of all, how will you achieve it? Okay. And but it's simple if you know what is called the normal of the plane. Okay. Or it's simple if you know what is the orthogonal vector to the plane. So what is meant by orthogonal vector? You have a plane, you want a vector that is perpendicular with the plane in this sense. So it is sort of, if this is your plane, then it is sort of shooting through outside the plane. Because if you hold the plane from side to side like this, you'll see that the vector is perpendicular to it. Okay, so that is what we mean by the vector is perpendicular to the plane. Okay, you need that. Now, how do you come up with it? That is the first question. But once you have the projection, it's simple. Once you have the projection, it's simple. Sorry, what am I saying? Once you have that normal, then it is simple. Okay, you just need to find a component, and that's all. But question is first, how will you find this? So given the equation of a plane, can you find the orthogonal vector to it? Okay.
Of course, on a plane, we can have a vector with 90 degrees. That's sure. But I think we need to have a formula which states that theta should be 90 degrees. I'm not sure about the formula. How.
Okay. So here I'll tell you a simple trick. Okay. And for example, this guy is perpendicular to the plane. Okay. And let me name him
N.
okay. N. Okay. N, no?
No.
Okay. So let me name it N. You can always look at a plane ax minus by, ax plus by plus cz equals 0. The vector ABC will, and this is my plane P. Okay. Plane P. Vector ABC will be always orthogonal to plane P equals ax plus by plus cz equals 0. This is something that you can remember also, but I'll tell you also what is the idea behind it. Okay, so what you do is you just simply pick its coefficients and make a vector out of it, and you'll be done. Because ax plus by plus cz equals 0 is somewhat like taking ABC and doing a dot product with xyz. And so this is somewhat like what is happening. So you are taking ABC transpose times dot product times xyz equals 0. And but what is actually happening? You're computing the inner product now. And but okay, so don't think of the transpose definition. It's simpler this way, I think. Anyhow, you're doing the inner product. So what does it mean when inner product is 0? If there are two vectors and the inner product is 0. Two vectors uv, then inner product is 0. What does that mean?
So they're
One vector
orthogonal
is
to each other.
perpendicular to the other vector.
Yes. Yes. One of the vector is perpendicular or vice versa. They are perpendicular to each other. They are orthogonal to each other. So this means this restriction ax plus by plus cz equals 0. Okay, when this equation is written this way, it means that all those x, y, z's, okay, what x, y, z will satisfy this equation, all those x, y, z's, such that a, b, c vector will be orthogonal to that x, y, z value. I want those x, y, z's which are in the plane. So what does that mean? This means that all points x, y, z on plane P are orthogonal to ABC, vector ABC. Okay. So it's equivalent to saying that. So therefore, it means that since all of the points are orthogonal to ABC and ABC is orthogonal to all the points on this plane, it means that ABC is perpendicular to the plane. Clear?
See, one question here. Okay. So let us suppose we have a plane. Okay. Can we say, suppose all the points on that plane can be perpendicular to a vector, providing vector's inclination.
All the points.
So let us suppose we have take a plane. We will have a infinite points, right?
Oh yeah. So sorry, I did not mean. So it does not make sense to say orthogonal to a point, because a point is does not have dimension. So it's actually all the vectors. Now it will address your question, Kishore, I think. Because now think of them as vectors. This is a plane. This is the origin. There will be points, of course. But what will be all the possible vectors on this plane? It will look like this. You get it?
But see, x, y, z are the vectors. We understand that, but there should be some condition to verify that vector is an orthogonal, right? So it should be the same thing, right? When we multiply it, the inner product should be 0. That vector will be
exactly that particular ABC.
Okay.
Okay. So and that particular ABC is this, which is perpendicular to every point. You get it? No matter where I keep it on the plane. So that is your ABC. So in this case, what is my ABC? It is 1, -4 and 2. So in this case, n is 1, -4 and 2. Okay. So this represents the perpendicular to the plane. Okay. Now the idea is pretty simple. Okay. So all I need to do is the following. I need to, so let me slightly modify it so that you can distinctly see what is happening. Let's say this black vector, okay, which I want to project, the project orthogonal projection on the plane. Okay. Let's say it looks like, let's make it blue actually. Okay, let's say it looks like this. What do I want? I want its shadow on the plane. And this is my point Q. Okay. Q of what? Q of U. This I want. But now what do I know? I know what is it. All I need to do now is project U onto this guy. Okay. If I project U onto the red, which is the perpendicular, I will get, what will I get? I'll get this, which I'm showing by green. This is the projection. What is the green part? The green part is the projection of U onto the normal of the plane N. Okay. Projection of the point U onto the normal N. Then all I need to do is move these steps back. Move these steps back. Let me, yeah, and then get this point. That's what I need to do. Okay. So, or rather, you can think of me. So you have this point. Now, what I want to do is I get this vector. After projecting, I get this vector. Now I want to reach Q. So all I do is, in other words, I will subtract from U that projection. So what does that mean? That by that amount, I'll move in the opposite direction and reach Q. Is that clear? So that will give me Q. Of course, that will give you a vector that is, I mean, the arrowhead is at Q, but it will that it has a direction also. But you know, the components of the vector will give me the point where it will fall, the shadow. So that is, yeah.
This is same as parallelogram. We can put it in terms of parallelogram as well, right?
Can you do it in terms of parallelogram? That is a good question, but how do you achieve it in terms of parallelogram?
Because in parallelogram also we are taking same. We have two vectors and then we are reflecting that onto the other side of the two vectors, and then we are making a parallelogram.
Yeah, but that is to compute the area, no? So this is like an intermediate step to prove the parallelogram theorem. But to use the parallelogram to get to this, that would be kind of opposite, because you already have, let's say you have the area of the parallelogram. Then do what? How do you get Q?
So here the agenda is to know the exact vector which is perpendicular to the plane, right? Okay, so but what we are doing is having two vectors and then projecting that into from the onto the plane and not to the other vector. We are doing in the both ways.
So yeah, because the problem here is if you have a plane, okay, and you have a vector and you need to project it on the plane. Okay, question is how will you do it? Okay, that is the problem. That is the problem. Where will the projection fall? So the idea is that the idea is that now let's say the plane passes through the origin, which is important because we need to know the formula. I mean the per normal of the plane. So the idea is that you find the normal of the plane, and then you find the projection onto the normal first. Okay, because this normal is perpendicular to the plane. You find the projection onto the normal first.
Sorry, just to interrupt. Sorry. When you say normal, it is just the vector with 0 degrees where exactly it falls. Is that?
No. A normal is a vector which is orthogonal to all the vectors that lie on the plane. Okay, so that's what I meant by this. So look at this plane. There are so many vectors that lie on this plane, no? And
the red one is normal.
The red one is the normal because it is perpendicular to all the vectors that lie on the plane. Is it not? Right, you get it.
Okay. So can I say, just for my understanding, irrespective of the the direction of the vector, and then where it exactly in which plane the vector has its location, the plane vector will be in on the other plane. I mean, sorry, the normal vector will be on the other plane, right? On the direction of other plane.
What do you mean by other plane?
I mean, like x, y, z we have planes. Okay. So the vectors will be, let us suppose, on the x plane.
Okay. XY plane.
XY plane. Okay. So the normal vector would be on the same XY plane, or it would be pointing to z plane.
Z plane.
Because to be perpendicular.
The z axis, yeah, to be perpendicular. Okay. So, but as you rotate, you can imagine the normal also rotating. Yeah, I mean, if you rotate the plane, you can imagine the normal also to be rotating.
So even then, the normal lies on the third plane, right? Third axis.
Yeah, it lies on the third axis. I mean, no, but then you can't really say that the plane exactly lies on the xy axis. No, now it is in between.
If the vectors are xy, then the normal would be an z. Then if the vectors on xz, it will be on y.
It will be on y. But if it is like this, it is a combination of x, y, z. Then even that normal will be a combination of x, y, z.
Oh.
Okay. So that's the idea, and the idea is that now that you have found the projection here, all you need to do is reverse it. So what is the projection here? So this is the projection of u on n, and all you need to do is starting from u, you need to go the same amount of distance that the projection tells you in the opposite direction. So you need to do minus projection. So all you need to do is this guy is u minus projection on n by u. Okay, so that's how you do it, and you know what n is. N is what? N is 1 minus 4, 2, and what is the formula for projection? Projection of n hat u would be equal to I had written this formula last time. Okay, dot product. Okay, n divided by n times n times n. So you can cancel this off. Okay, and so this will give you the projection. Okay, and you know what u is also, so you can calculate it offline because it's almost time. So u is 104. Oh, actually, in the question it's written v. But anyhow, do this, plug this into this, and then apply this formula u minus position, and you'll get the exact point where the shadow falls on the plane. Okay. So having said that, I think I'll end this session. Okay. What could we not do? Okay, we couldn't do this volume problem, but it's just a matter of determinant computation. So it's just a lot of formulas in this week's content. So conceptually, I would say that it's just an introduction to 3D linear algebra. So in the coming weeks, we'll explore more into eigenvalues in 3D and such kind of concepts. Okay, but if you have any more questions, then just let me know. Else we can wind up, I think. Yeah, hi, Mr. Shukla.
Here the vector v is 104.
Yeah,
Since the y component is 0,
yeah.
we can say the vector is lying in xz plane. Am I right?
Yeah, okay, yeah, that's right. Yeah, it's lying on the xz plane. That's correct.
Xz plane.
That's right.
Thank
That's right. So, is it going to? Okay, but this plane is still some non-trivial plane. So actually, our vector will look something like, okay, where is the exact plane? This is z. This is this is z. This is x. So yeah, the vector will lie here. That's correct. The vector will lie on this plane. That's right. Yeah. Okay. Okay. Maybe next week I'll do a simulation of this. I'm actually still looking for a good simulation software to demonstrate this, but I'm not yet getting it unless I code in I don't know, Python or something maybe. So
basically, matplotlib would be the right API.
what math?
Matplotlib. It's one of the library files.
Oh, matplotlib. Yeah. I'm thinking whether I should go with matplotlib.
But we need to code it. We need to code it basically.
Yeah. I mean,
because let me check. One of my in one of my course, I have the source code. Probably I'll check whether I have it in my what do you say in my records. If possibly if I find it right, I can mail you.
Yeah, code. Sure. Great. Okay, great. That sounds good. I mean, the only issue with matplotlib I've had is I was thinking of is well, I mean, when I mean, just plotting vectors is fine, plotting planes is fine, but when I combine them, strange things start to happen. Sage math is also there, yeah. I have a very old Sage math server running here.
So basically, what I observed with the matplotlib is once we plot and then execute or compile or execute that code, right? So we get an editor which shows in a front view, and then if we wanted to rotate the plane or we rotate the coordinate system, everything, those options will be visible on that editor itself.
Oh, I mean, it's not there with whatever versions I'm using. I mean, what editor are you using?
No, it's not editor. It automatically once we plot and then once we execute that Python code, right? It automatically opens, and the editor for that Python code is Google Colab.
Google Colab. Oh, you are able to do that?
Yeah, I have seen this on that Google Colab, but sometimes what happens due to the server of Google, it may not properly. We face issues on that.
Oh, I mean, that's actually wonderful. But I was doing in Jupyter, but I could not do that. I mean, I'm not
even
in.
Also, it it happens. But as it is on the local system, right? Probably that might be the cause. But when we do it on Google Colab, right? Probably because they have a very high infrastructure.
Could be, yeah, yeah, yeah. And anyway, yeah, it's been quite some time. I don't usually code because I work in a very theoretical field. So,
Okay. So
uh,
basically, when we were working on the computer vision algorithms, right? We have used this.
oh, okay, interesting. Okay. Just mail me the resource
Yeah,
once.
I'll try to find out, and then once I find, right, I'll share the code.
Sure. Because it'll be nice to visualize actually.
Yeah, basically, I think what we need to do is just change the plotting points so that it will show us the some visual.
That's right. If there is a nice way to draw vectors as well as planes and lines on the same place, then it'll be really convenient. Yeah.
Sure, I'll do that.
Okay. Great. Yeah. Anything else?
Yeah, thanks very much.
Oh.
Yeah.
Okay.
Thank you so
Okay.
Thank you all.
Bye. Good night.
Okay.
Good night.
Okay
Good night,
then.
everyone. Bye.
Okay. Thank you. Bye bye. Yeah. Hi, Mr. Shiv Kumar. Should I?
Sir, I registered for the exam.
Oh, great. Okay.
And last Saturday, I bought this book, Linear Algebra Linear Algebra, Pure and Applied by Edgar G. Goodare.
Edgar G.
Saturday, Goodare, and
Okay.
started reading.
Okay.
He is written he's a professor from university in Canada. Memorial
okay.
University in Canada. The first chapter, that Euclidean n space, I have read,
Okay.
and it's quite understanding.
Okay.
And I will read this book and appear for the exam.
Oh, okay.
And
Nice. Okay.
while writing the sentence, I made a mistake. I wrote only Bangalore and Tumkur and Dharwad.
Oh no.
I
Okay.
should have written Madras because I did MTech from IIT Madras. I could have seen the IIT
nice
after
one.
1984 passed out.
Oh, nice. That's
I would
nice.
have come
Wonderful.
back to, in the pretext of this exam, I could have come to Madras and seen IIT.
Oh
I made a
yeah.
mistake.
Oh, nice. We could have met also. Oh.
I have written Bangalore as the center. Will they be conducting in Bangalore or it will be only Madras?
No. I mean, it'll be the exam itself will be all across different centers, whatever choice you've put.
Oh, I see.
But if I think since exams are a long way from here, you can still email them and get the center changed. That's what I think. Because exams, there's still quite some time, right? Probably.
November 1st they have written.
Yeah. November 1st means like they
That is there no
should not have a problem with changing the centers.
Okay.
Yeah. You
will
could
try.
mail them once. Yeah. So which department were you from?
I'm from electrical engineering department.
Oh, okay.
Now retired.
Oh, okay.
Retired in the year 2022, May. I retired.
Oh, okay.
So I was just doing tours and all those things.
Oh, nice.
In June, I went to Europe tour and all.
Oh, that's
Now
wonderful.
I feel I'm wasting time. So I registered for your course and started learning linear algebra. Because during my PhD program also, one maths compulsory subject was there.
Yeah.
That is, I had registered for linear algebra, but somehow due to work pressure, I dropped this course in the first semester of 1998, August, December in Indian Institute of Science. I did PhD.
I see. Oh, nice. Okay.
In 2002, I completed.
Oh.
And thereafter, faculty in University of Visvesvaraya College of Engineering, Bangalore.
Okay.
From 2002 to 2022, 20 years I taught there.
20 years. Okay.
20
Nice.
years
That's
electrical engineering subjects, and that electromagnetic field theory number of years I've taught.
Oh.
So this cross product, dot product, every time we have taught to the students.
Oh,
That's
right.
how I remember. But this mathematics basics, I didn't know much. I think this course will make me learn. And you are
Yeah.
going in a very systematic way, and I'm able to understand almost
Mm-hmm.
all, 100%.
Yeah. I mean, I am also myself learning side by side. uh, I mean, I work in computer science, theoretical computer science, and sometimes I need to use linear algebra, but I don't need to use a lot of linear algebra. So I'm also, you know, learning while I'm taking the tutorial side by side. So it's been a nice learning opportunity for me also at this moment.
You're doing PhD there?
Yes.
Who is
So
your guide?
my guide is Professor Jalal Sharma. So well,
Okay.
you may not know him. Uh,
No, when we were doing MTech, computer science students, we had friends in the hostel. No,
okay.
hostel. I was in Alakananda hostel.
Oh, okay. Okay, it's
Friends used to be there who was doing computer science.
uh,
They were telling that Kalyana Sundaram was there,
oh yeah.
or that, what is that, finite, automata, and formal languages,
Oh yeah,
and
yeah, yeah.
all your computer science subjects.
Yeah, that's
So
right.
he used to conduct entrance. He used to conduct an entrance test and then only allow for registering.
Okay.
So we students in electrical block
Huh.
were not allowed there because the test used to be very tough.
Oh yeah.
The-
Oh, okay.
like that. But it was a nice 2 years in IIT Madras.
Huh.
After that, I got placement in HMT R&D. That is research and development.
Oh,
I was
okay.
put in the CNC machines design.
Okay.
So